Hello folks, we're going to look at solving and graphing trig equations. It's 10 o'clock at night, which means I am adequately tired and ready to go. This PowerPoint has 40 slides, which means this is about to be the longest thing ever. So we actually looked at these two problems on the last video, but let's run through them again real quick because we need to use two ideas here. First idea is that we need to use a cofunction identity. That will allow us to change secant of pi over 3 into cosecant of pi over 6. And then we need to use a Pythagorean identity. So remember that cosine squared plus sine squared equals 1. And then we can subtract cosine from both sides to get sine squared equals 1 minus cosine squared. Notice we have 1 minus cosine squared right here, so we can replace that with sine squared of that angle, which is pi over 6. So we have sine squared of pi over 6 times cosecant of pi over 6, and they're multiplied together. But what is cosecant? Well, cosecant is the reciprocal of sine. So we have a sine squared pi over 6 times 1 over sine squared of pi over 6. They cancel out, and we're just left with 1. So the answer to that problem is just 1. That's kind of cool. Let's look at this next one real quick. Similar idea here, going to use some identities. We just saw here that 1 minus cosine squared is the same as sine squared. So that numerator I'm going to replace with sine squared of pi over 4. And what is secant squared minus 1? Well, let's just come up with it real quick. We have cosine squared plus sine squared equals 1. How do we get secant? Well, secant is the reciprocal of cosine. So if I divide everything by cosine squared, I'll get another identity. I'll get 1 plus tan squared theta equals secant squared theta. And now I can rearrange that to get secant squared theta minus 1, cross that off, equals tan squared theta. So that denominator is just going to become tan squared of pi over 4. But sine squared of pi over 4 over tan squared of pi over 4. Well, think about what tan is. Tan is sine over cosine. So I can write that as sine squared pi over 4 over cosine squared of pi over 4. Dividing by a number is the same as multiplying by that number's reciprocal. So I have sine squared of pi over 4. Instead of dividing it by sine over cosine, I'm going to multiply it by the reciprocal, which gives me cosine squared pi over 4 over sine squared pi over 4. My sines cancel, and I'm left with cosine squared of pi over 4, which we can evaluate, because we know that cosine of pi over 4 is root 2 over 2. So if we square both sides, we get square root of root 2 is 2, square root of 2 is 4, we get 2 over 4, so we get 1/2. So that is our answer for that messy thing. It just became 1/2. So understanding how to use identities is a hugely important concept in this unit. Let's look at two new ones now before we go. Notice we have like uber fractionage going on here, lots of messy stuff. So let's look at this supernumerator right up here. Typically, when you're dealing with two separate fractions with weird things that you don't know how to handle, it's a good idea to find a common denominator and multiply them together. So our common denominator is going to be sine theta cosine theta. So we need to multiply this side by cosine theta over cosine theta. And that's just equivalent to 1, so we can do that. And we're going to multiply this side by sine theta over sine theta. And so, what do we get? Well, in the top there, we get sine squared theta, sine times sine, plus in the top over here, we get cosine squared theta. And all of that is over sine theta, cosine theta, and all of that is over 1 over sine theta. But what is sine squared theta plus cosine squared theta? Well, that's just 1. That's the Pythagorean identity. So we get 1 over sine theta cosine theta. Instead of dividing by 1 over sine theta, I'm going to multiply by its reciprocal. So I'm going to multiply by sine theta over 1. And look what happens. Sine and sine cancels, and I'm left with 1 over cosine theta, which, that doesn't look like a theta at all anymore. It is 1 over cosine theta, which we should write as secant of theta. So again, that huge ugly thing was actually just a really strange way of writing secant. Crazy. 1 last 1. Cosine squared x plus cosine squared x tan squared x. Well, typically when you have two things multiplied together, it's a good idea to write them out in terms of their identity. So think of the quotient identity for tangent. We know tan is sine over cosine, so I can replace this tan with sine squared theta over cosine squared theta. Oops, sorry, we're dealing with x's, not thetas. So I should stay consistent there and call those x's. But look at what happens. Cosine squared x and cosine squared x. So we're left with cosine squared x plus sine squared x, which is the Pythagorean identity. So we get 1. So now we're going to look at a few problems on the learning guide just to start thinking about how to solve them, getting us toward thinking about graphing functions. We have some weird equations here, and we want to solve them for theta. So let's think about what we know. I want to solve this for theta, so I'm going to start getting that cosecant function by itself. So I'm going to add 2 to both sides to get root 3 times cosecant of theta equals 2. Then I'm going to divide both sides by root 3 to get secant of theta equals 2 over root 3. And at this point, you might be thinking it's a good idea to rationalize that denominator, but I'll do you one better. Cosecant's reciprocal is sine, so I can rewrite this as sine of theta, the reciprocal on the left, equals the reciprocal on the right, which is root 3 over 2. So we're looking for all the solutions between 0 and 2 pi, that where sine of theta equals root 3 over 2. So as we typically do, let's draw ourselves a little fake unit circle. So where is the value of sine root 3 over 2? Well, that happens right there at pi over, not 6, sorry, pi over 3. The y value there is root 3 over 2. I remember that sine of pi over 6 is 1/2, and the other one is root 3 over 2, so that flips me up to the pi over 3 up there. Again, you need to be familiar with the unit circle in order to do these problems. So that one right there definitely gives me root 3 over 2, but what else? Well, sine is the y value. That right there, 2 pi over 3, also has the same y value right there. So we get two solutions for theta. We get pi over 3, and we get 2 pi over 3. Cool. Let's do another one. 2 cosine theta plus 4 equals 3. Again, let's isolate the trig value. So 2 cosine of theta equals, subtract 4 from both sides, equals -1. and divide by 2 on both sides to get cosine theta equals -1/2. And again, now you just need to figure out where is cosine equal to -1/2. Well, we actually end up with that same 60-degree reference angle right there, giving us this 2 pi over 3, gives us a cosine value of -1/2, and so does this point down here. So we have 2 pi over 3, and we have 4 pi over 3, so we've found our two theta values, 2 pi over 3 and 4 pi over 3, that give us a cosine value of -1/2. So those are the solutions to that original equation. So, as you can see, you need to be very familiar with the unit circle. Let's do one last one, and then you can try the rest on your own, or watch those learning guide videos when I put them up in a little bit. So, notice right here, notice what we can do here. We have a sine squared, and we have a cosine. It sure would be great if we were dealing with the same function here, because then maybe it would be something we can factor. So think about what we know. We know that sine squared plus cosine squared equals 1, which means that sine squared is the same as 1 minus cosine squared. So I can replace that sine squared with 1 minus cosine squared. So I have 1 minus 2 times 1 minus, sorry, not sine, cosine, cosine squared theta plus cosine theta equals 0. So let's distribute. 1 minus 2 times 1 is 2. Negative 2 times negative cosine squared gives me a positive cosine squared theta, a positive 2 cosine squared theta, and I have plus cosine theta equals 0. So let's combine like terms and simplify. I get 2 cosine squared theta plus cosine theta, and then I have that 1 minus 2 gives me a -1, and this is all equal to 0. So, hopefully you recognize that this looks a lot like a quadratic. Imagine that we had just the quadratic here, 2x squared plus x minus 1 equals 0. So really what we're saying is let x equal cosine of theta. We're making an algebraic substitution to make this math a little easier. Well, how do we factor this? It's going to get a 2x there, an x there, and then what? We need our numbers to multiply to 1, so they both have to be 1, and which one's positive, which one's negative? Well, we need to get a positive x, so that tells me this needs to be positive and this needs to be negative, because when I get the 2x times the 1, I get a positive 2x, the negative 1 times the x is a negative x, so we get our positive x like that. But this then is going to be the same way that cosine factors. So think about this. Let's continue to solve this. If 2x minus 1 is a factor, then whatever x value makes that 0 gives me a 0. So I'm going to get x equals 1/2. And over here, if I have x plus 1, I'm going to get x equals -1. But now we need to substitute back in and solve this for theta. So if x is cosine theta, really I can say cosine theta equals 1/2 and cosine theta equals -1. Well, where does that happen? Draw yourself a little reference circle. Cosine of theta is 1/2, again, up there at pi over 3. It's also 1/2 right down there. And what angle is that? That is 5 pi over 3. But we also need to know where cosine is -1, and that happens straight out to the left at pi. So I have 3 solutions for theta. I have pi over 3, I have pi, and I have 5 pi over 3. At this point, I would recommend you look at some more of those problems and try and figure them out. They're all going to work in similar ways. It's just figuring out how to piece all of this lovely information together. All right, so that's all we're going to do with identities for now. Now we're going to look at graphing sine and cosine. So objectives, be able to graph sine and cosine functions. And again, we want to think of these as transformations of a mother function, just like we normally do. We're really going to focus on sine because everything we do with sine is going to work for cosine as well. So think about what we know on the unit circle. Think about easy points that we can graph on the unit circle. And when I say easy, I mean super easy, like these points right there. So what are the sine values of these points? Well, sine is y, so the sine value here is 0, here it's 1, here it's 0 again, and here it's -1. So let's translate that to a graph. What are these angle values? Well, the angle value here starts at 0, and then we get pi over 2, and then we get pi, and then we get 3 pi over 2, and then we get back to 2 pi. And we could keep going around forever. But what I do when I graph these is I just start there, I put my period, which is 2 pi. You don't know what that word means yet. Maybe you do, I don't know. I split it in half. There's my pi. I split that in half. There's my pi over 2. And I split that in half. There's my 3 pi over 2. I'm going to label that as 1. I'm going to label that as -1. And now all I have to do is plot these points. So sine starts at 0. And then at pi over 2, it is up at its maximum value of 1. Then it comes back to 0 at pi. Then it goes down to its negative value, and then it comes back up. So hopefully you can see that shape, and we can sketch in a little curve to represent our lovely sine graph, sine of theta, or let's just say sine of x, since now we're just talking about real values on the number line. So that's your basic sine graph. Sweet. Let's talk about some stuff now. The period of a sine graph, aka how long does it take until your sine values start repeating? Well, we sort of just talked about that. Think about it. We start here, and we have to go all the way around the unit circle until that pattern of values starts to repeat. And, well, how long did that take? It took 2 pi. So another way of thinking about it is how long does it take to get back to where you started from? Well, we started here where our sine graph was then going to go up. How long does it take until we're back at that 0 with our graph about to go up? Well, it takes until we get to 2 pi. We could continue this down like that, and then we could now say we're looking at 2 periods of this graph, and this would be 4 pi right there. Another good way to remember it is peak to peak, because we go to peak to peak. So go from the 2 peaks of that mountain, and that is your period. But I think that's a little bit harder, because then you need to think of this as 5 pi over 2 minus pi over 2 gives you 2 pi. I would just think of it as this 0 to that 0, but really I just think of it in terms of the unit circle. I think that makes it the easiest. So a couple questions here. First one was, what is the period of sine of x? Well, we just said that that period is 2 pi. Think of that as your standard period. Well, what about if we're dealing with y equals sine of 2x or sine of 2 theta? Well, think about what's going to happen. If we're dealing with the unit circle, imagine I put in an x value of pi over 2. Normally, that would get me straight up and down. But since I'm dealing with 2 times x, I get 2 times pi over 2 is pi. So when I put in that angle, I go twice, as far. Instead of going from there to there, I'm going all the way to there. So, if you think about this, I'm moving through the unit circle twice as quickly, which means it's going to take half as long. And that's kind of weird. But think about this. If I put in pi, so if I put in x equals pi, what do I get out? I get 2 pi. So by going to the value of pi, I actually go all the way around to where I'm going to start to repeat again. So the period of y equals sine of 2x, the period, which is denoted with a t, you can think of it as time. How long does it take to get back where you started? The period has to be half of what I started with. So instead of 2 pi, it's pi. Think about mathematically how we get from 2 pi to pi. We took that normal period and we divided it by 2. Where did that 2 come from? The 2 came from that coefficient right there. Okay, well, what about sine of x over 2? It's going to be the same idea. I'm going to erase all this stuff real quick so we can think about this from a clean slate. Let's do the same thing. Let's think about this in terms of the unit circle. So imagine now I put in the x value of pi. So normally that would get me all the way there. But I'm dividing it by 2. So instead of going all the way there, I'm only going halfway there. Okay, well imagine I put in 2 pi. Normally that's 1 full revolution, but I'm dividing it half, so I'm only actually going to get halfway there. So how long is it going to take me to go all the way around? Well, it's going to take me 4 pi, because if I divide that by 2, I get my normal 2 pi, which is where I will start to repeat values. So the period here is 4 pi. And again, what's the connection between that coefficient, which is actually 1/2, and that 4 pi? Well, we took our 2 pi and we divided it by that coefficient. Dividing a number by 1/2 is the same as multiplying that number by 2. So I get 2 times 2 is 4 to get my 4 pi. So that bottom question there, what's the formula to find the period of the sine graph? If we are multiplying that x value by something, well, we take the normal period, which is 2 pi, and we simply divide it by that coefficient. And that will tell us our period t. So, let's think about how to graph this real quick. First thing you should do is figure out what your period is. So take that 2 pi, divide it by the coefficient. 2 over 4 is the same as 1 over 2, so my period is pi over 2. Okay, well, what does that mean? Well, it means, now that we know the period, this is going to be really easy to graph. Think about what we did all the way over here. First thing I did was I plotted that 2 pi, which is the period. So I'm going to do the same thing. I'm going to plot the period over here, which is pi over 2. And now I'm again going to split this up into 4 equal pieces. Halfway is going to be my total period divided by 2. So it was pi over 2, so that's pi over 4. Go halfway again. Now I'm dividing by 2 again. I get pi over 8. So if I get 1 pi over 8, 2 pi over 8, this has to be 3 pi over 8 right there. And then again, think about what the sine function does. It starts at 0, it goes to its highest value of 1, goes back to 0, goes to -1, and goes to 0 again. That pattern is going to be exactly the same. Boom, boom. I'm going to start at 0, I'm going to go up to 1, I'm going to go down to 0, I'm going to go down to -1, I'm going to go back up to 0. So, notice that this looks exactly the same as that first thing we did, but it's not the same. The scale on my axes is different. And you need to show me that, otherwise I have no idea if you know what you're doing or not. So, have to show me that scale. Okay, so now let's think of a different situation. No, let's do one other problem real quick. There's a billion pages already that we're going to work through, and I'm adding one on the fly. Why am I doing that? Well, I want you to learn this stuff. So, let's think of this. What if we're dealing with y equals sine of, how about, let's go x over, no, let's make it trickier, x over 3. Okay, well, x over 3 is really, we're saying the same thing as 1/3 times x. So our coefficient is 1/3. So take the normal period, 2 pi, and divide it by the coefficient, 1/3. So dividing by 1/3 is the same as multiplying by 3. So I get my period is 6 pi. So again, super quick at this point. 6 pi right there, go halfway, we get 3 pi, go halfway again, we get 1.5 pi, which I'm going to write as 3 pi over 2, because then I can say 3 pi over 2, 6 pi over 2, and 9 pi over 2 right there. And I'm going to do the same thing. I'm going to get that point, that point, that point, that point, and that point, and I'm going to sketch it in. And I'm done. It ain't no biggie. So, let's look at this one now. Find the period of this graph. You may be like, oh no, it's got a pi, that's going to make it hard. But it's not. Take your 2 pi, divided by the coefficient, which is pi. Look, the pi's cancel, and it's easier. The period is 2. So, here is 2, halfway is 1, halfway is 1/2, 3/4 of the way is 3/2, and again, boom, 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 boom. Holy moly, that was super easy. Okay, what about this one? Getting a little trickier. Last one here before we move on to the next idea. So let's go ahead and take our normal period of 2 pi and divide it by our pi over 6. What's going to happen? The pi's are going to cancel, the 6 is going to move up, and we're going to get a period of 12. Nuts. So, boom, 12, boom, 6, boom, 3, boom, 9, boom, 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 whoa. And I'm clearly doing this super quickly because we have a lot to do and I'm really tired. But the ideas are all there. Just make your graphs neater than mine. Okay, so that is your period. And now I want you to think about how these two functions differ. Look at the blue function, which is that normal y equals sine x. Look at the red function, which is y equals 2 times sine x. How do they differ? Well, again, think about those key points. Instead of going up to +1, it goes up to +2. Instead of going down to -1, it goes down to -2. All of the other points are also multiplied. All it does is stretch your function up and down. The zeros are exactly the same. The starting point is exactly the same. The period is exactly the same. The only gosh darn difference is that it goes to a +2 and a -2. That is the amplitude of your function. So it's half the distance between the peak and valley of the graph, which is a fancy way of saying it is that distance right there. Okay, whoa, missing stuff. What is the amplitude of sine x? Well, the normal amplitude is just 1. So what's the amplitude of 2 sine x? Well, it's 2 times the normal amplitude, which makes it 2. How can you tell the amplitude of a trig function based on its equation? Just look at that coefficient right there. Well, what if it says y equals -3 sine x? Well, the amplitude is actually still a positive number, so think of it as the absolute value of the coefficient right there. And that'll be a good definition. Okay, so let's look at some problems. Let's think of the amplitude, and let's graph it. So the amplitude is 3. This is a normal sine graph, so my period is still 2 pi. So let's quickly graph this. Boom, 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 boom. 2 pi, pi, pi over 2, 3 pi over 2. The only difference in how I sketch this, I'm going to make it look exactly the same at this point. The only difference is I need to label this as a positive 3 and this as a negative 3. Holy moly, that is not a big deal. Let's do another one. Well, what if we throw that negative in front of it? So I'm going to do 2 different graphs right here. First thing I'm going to do is I'm going to graph this normal sine graph right up here. And that is going to look like that. It's going to continue on forever, but that's all I'm showing. That's the normal sine graph. Well, what happens when you plop a negative in front of a function? What happens if you have y equals x squared and you plop a negative in front? Well, you get a flip in the vertical direction. It flips over the x-axis. This is going to be the same exact thing. So, if we split this up, just like we did before, instead of going to positive 1 first, it's going to go to negative 1 first. Instead of going then to negative 1, it's going to go to positive 1. So it's going to be a perfect mirror image reflection across the y-axis. But again, key idea, notice all the zeros are exactly the same. Okay. Well, what about this one? Mr. Reed, you're getting tricky. Well, remember that sine is an odd function, which means sine of negative x is equivalent to negative sine of x. So I can pull that negative out and rewrite this as y equals negative 4 sine of x. And now we can quickly graph this. Instead of going up first, it's going down first. So we get those points. And what are these values? Negative 4 and positive 4. And then you can sketch it in. It's done! That's it! Okay, so next thing we need to talk about is the phase shift, aka horizontal translation, moving it left and right. It's going to work exactly the same way as normal functions do. So, what can we do? Well, think about this. If I have the square root of x minus 2, what does that do? Well, that takes your normal square root graph, which looks like that, and it shifts it to the right by 2. Remember, the minus 2 shifts it to the right by 2. So I go boom, boom, and then it looks exactly the same. Well, it's going to do the same thing here. So if I have sine of x minus pi over 2, well, that's going to shift my graph to the right by pi over 2. So do I have one here? Okay, let's look at this one real quick, and then we're going to go back to the other questions on that page. So if I have, this is how I think of this problem. I do the same thing. I see there are no other transformations. So I think of the normal, well, that's not what I want. I think of the normal, this is poopy. I'm going to start that over. Boom, 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 boom. That's a little bit better. So normally sine is going to go start there and go there and go there and there and there. But we're shifting this to the right by pi over 4. Well, let's label this because we need to figure out where pi over 4 is. So that's pi over 2. That's 3 pi over 2. So notice my scale currently does not have pi over 4 increments. So I need to split these in half because now it does have pi over 4 increments. And now I think of it as just shifting every single point over by pi over 4. So that goes there, and that goes there, and that goes there, and that goes there, and that goes there. Because now I can quickly go boop, and it's a little awkward. We should continue this down like that, because it'd be weird to just start it in the middle there. But that was not bad. All we did was shift it to the right a teeny tiny bit. Okay, well, now we need to think about something a little different. I'm going to skip that middle question and go to that last question there at the bottom, because you need to think about, how does this function up here, how does that change when we throw that negative in front? Well, you may remember that that negative is a horizontal reflection. It is a flip about the y-axis, and it not only does that, so it not only is going to make that square root open that way, it's also going to change that -2. Instead of moving it to the right, it actually moves it to the left. So I get 1, 2 like that, and then my graph opens like that. And why does it do that? Well, you should think about factoring the inside. When you get messy stuff like that, always factor the inside. We can factor out a negative, and we get x plus 2 like that, because now we see the x plus 2, and we can say, okay, well, it's shifting it to the left like we normally think of it, and it is also reflecting it with that negative, flipping it around. Cool, cool, cool. Neat stuff. Same exact thing here. If I have a negative x minus pi over 2, we can factor that negative out, and you can think of this as x plus pi over 2. Well, you may be like, well, that's more complicated. But we know that sine is an odd function, so we can pull that negative out front. Negative sine of x plus pi over 2. And we can see that this is actually going to shift this graph to the left by pi over 2, and it's going to flip it upside down. So let's look at an example with that now. Okay, apparently not. Apparently not again. Okay, apparently there's not an example of that. So we are going to do this one right here. Okay, so notes from myself of things we need to do. So let's do this. Let's, again, start with a normal mother function and break it down into these different components. So normally we have 2 pi, pi over 2, and 3 pi over 2, just like that. But instead of the normal sine graph, we're shifting everything to the left by pi over 2. So what I'm going to do is I'm going to add another increment here to get a negative pi over 2, because then I can say, well, instead of starting at 0, I'm starting here. And then everything else is going to play the same way. But I have a negative out front, so instead of going up first, I'm going down first. So I'm going to hit my first point there, and then everything else is going to follow that same symmetrical pattern as we've seen, and there's my graph, and I'm done. If I want, I can continue it. It doesn't really matter, because it's going to go on forever. There's no stopping point. So we did it. That is really cool. Simplifying things algebraically first makes them way easier. So now that we did that one, the next examples we look at are going to be like, psh, piece of cake. So let's do them real quick. Let's make them cake pieces. So again, 1, 2, 3, 4, 2 pi, pi over 2, 3 pi over 2. But, now we're shifting everything by pi's over 6. Well, how many pi over 6's are there in pi over 2? Well, there are 3 of them. 3 pi over 6 is equivalent to pi over 2. So, I need to break each of these down into 3 pieces. So add 2 little tick marks in between each little interval, because then I have 1 pi over 6, 2 pi over 6, 3 pi over 6 is pi over 2. Okay, Well, what can we do now? We're shifting it to the left pi over 6, so I'm actually going to add one more little tick mark right there for negative pi over 6. And now, again, all we need to do is fill in the pattern that we know for the sine graph. We're starting here. Sine goes up first. So where does it go? Well, it's always going to be one tick mark to the left of where it normally is. So my next point has to be right there. And then my next point has to be right there. And then my next point has to be right there. And then my last point's going to be right there. And now we'll just sketch it in. Notice for all of these, like every single graph looks the same size. The only difference is the scale that we mark on each one is different. So when you're doing this, you absolutely need to mark your scale. Otherwise, we have no idea what you did. Whew, okay. We've done a lot. We're on slide 26 already. We're cruising. Not really. This is like already 30 or 40 minutes. This is going to be a really long video, which means we're not going to get through all this in class, but that's okay. Okay. Wow. One more. This is combining a modified period and a phase shift, but the idea is exactly the same. When you can, you should factor it because that's going to make it much easier to understand what's happening here. Sine of 2, I can factor that 2 out to get x plus, well, if I factored that 2 out, I need to divide that by 2 to get, because think about it, if you distributed the 2 back in, well, pi over 2 times 2 is pi, so we're good there. Okay, why did we factor it? Well, we factored it because now we can see that our period is going to be our normal 2 pi divided by that coefficient of 2 gives me pi. So I'm going to start again by splitting everything up and putting my period there. So then that's pi over 2, and that's pi over 4, and that's 3 pi over 4. Have you noticed yet that that third one always has a 3 in the top? Whoa, that's cool. And the denominator is always the same as that first one. Whoa, that's also cool. Okay, but then what is our transformation? Looking up here, you might say, plus pi means, hey, we need to move that to the left by pi. But the problem is that phase shift gets affected by that modified period. So you need to focus on this phase shift after factoring out that coefficient. So really, our phase shift is pi over 2. So we're adding pi over 2, which means I'm going to extend these axes over a little bit and give myself a negative pi over 2 right here. Okay, well, that means I can now start right here, and now everything else is gonna be exactly the same. Boom, 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 boom. And I can continue on. That's a full period right there, but I'm going to continue. Boom, boom. So I actually am showing 1.5 periods there. Sweet. Really, it's, you got to understand how these things work. But once you understand basically how they work, doing them is really quick and painless. All right. So we're going to talk about one last modification of the sine graph. Just like any other function, we can also shift the sine graph up and down. So let's think about y equals sine of x plus 2. Well, it's going to be the same exact thing as our sine graph. I'm going to start the same way. I'm going to go 1, half, another half, 3/4. And I'm going to say 2 pi, pi over 2, 3 pi over 2. But now everything is shifted up by 2. So what I'm going to do now is going to say 1, 2. So think about this. Normally there is a line of symmetry that goes right down the middle. That doesn't look very symmetric. Normally, there's a line that goes right, whatever. Normally there's a line that goes right down the middle that cuts your parabola in half. And normally that symmetry line is right on the line y equals 0. But everything's shifting up 2, including that line of symmetry. So I'm going to draw ourselves in a little line of symmetry to make this easier. No, that is not an asymptote. I'm drawing a line of symmetry because now I know that sine will start here and it will go 1 above it, and then it'll come back down. It will go 1 below it, and then it'll go back up. And then again, sketching it is super painless. Okay, let's do another one. Sine of x minus 3. Well, we're going to do the same thing. I'm going to draw some axes here. That's too curvy. I'm going to draw some axes. I'm going to go 1, half, quarter, 3/4, 2 pi, pi over 2, and 3 pi over 2. Okay, so what do? Well, let's shift that line of symmetry down 3. And then we're going to start, we're going to go up, we're going to come back down, we're going to continue to go down, and we're going to go back up. And then we get our little squiggly sine graph. That was poopy looking. Let's try that again, Mr. Reed. How's that? Is that still kind of poopy, but a little bit better? Okay. I'm not even going to do this. It's exactly the same, except it's up 4, and that's up 1. Totally not doing that. Okay, golly, that was a lot of stuff. But we need to think about this question. We did all of those with the function sine. How is cosine going to compare? Well, everything we talked about with amplitude, period, phase shift, and shifting it up and down is going to be exactly the same. The only difference is what cosine looks like. So, think about the unit circle. And again, think about these special points. We're going to split it up in the same way we did for cosine. 2 pi, pi over 2, and 3 pi over 2. Well, what is the cosine of 0? Cosine is x, so cosine now actually starts up here at 1. Okay, that's cool. Well, what about pi over 2? Well, cosine is 0 there, so it comes back down. What about pi? Well, it's -1 there, so now we're down at -1 right there. And then what about 3 pi over 2? Well, cosine is 0 again. It comes back up. And lo and behold, we're going to finish where we started, back at the top. And so we get this lovely looking thing right there. And notice that if I'm going to do something here, something crazy. I'm going to draw one more and continue this down like that. And now what I want you to do is I want you to picture, imagine if I put my, no, let's do this. I'm going to continue it over this way, okay? Right there, to negative pi over 2. Well, think about what I just did to this function to shift it to the right. Wait, no, that's, wow, what am I trying to say? I don't know. What I want you to notice is, imagine if I put my axis right there and graphed this. What did I just graph? That would be a sine graph. So, if you think about that sine graph, my axis is not there in that big blue-bitty line. My axis is right there. That, if you look at just between there and there, what have I done? I've taken a sine graph and I've shifted it to the left by pi over 2. So if I call that blue graph y equals sine of theta plus pi over 2. And that's the same exact graph. We get that as the same as my cosine of theta. Holy crapoly. It looks kind of similar to the cofunction identities that we explored yesterday, except notice the cofunction identity is a little different. The cofunction identity says pi over 2 minus theta gives you the cofunction identity. So it's a little different, but hopefully you can see how they are kind of super related. Sine and cosine are the same functions. They're just offset by a factor of a pi over 2. Crazy. So now we're just going to have general practice, and then I'm going to go to sleep. Let's graph cosine of pi over x. So let's figure out what our period is. So we take the normal period, 2 pi, divided by the coefficient. Pi's cancel. We get 2. So, boom, 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 boom. I can't do the booms as quickly when I'm writing fractions. Okay, well, where does cosine start? Cosine starts at its maximum value, and then it goes down to 0, and then it hits its minimum, and then it hits 0, and then it goes back up to its maximum. Could it be quicker? Okay. Oh, goodness gracious. What about this mess? Well, we got a lot going on here. First off, period is going to be 2 pi over 4. So pi over 2. So I'm going to start. Notice I have awkward axes now. I'm going to start. Boom, 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 boom. Pi over 2. Pi over 4. Pi over 8. 3 pi over 8. Look at that translation, minus 3. That's going to shift everything down. 1, 2, 3. So that symmetry line is down there at 3, so I need to go one more below it. Deep breath. And normally, cosine starts at its maximum, but I have a negative in front, so cosine now will start at its minimum. And I'm going to make this even easier. I'm going to put little tick marks there so I can line myself up a little bit better. So cosine now is starting at its minimum, and then it'll hit 0, and then it'll hit its maximum, and then it'll hit 0, and then it'll be back where it started. Oh my gosh, I'm really bad at drawing these for some reason. But there you go, you get a little mountaintop. And we could continue this on in both directions indefinitely. Okay, 2 sine of 2 pi x. What's our period? Always start with that. Period is 2 pi divided by the coefficient, which is 2 pi. So the period is 1. So we get 1, 1/2, 1/4, 1/8. And what does that 2 do? Well, that makes it so it goes up to 2 instead of going up to 1. But now we just need to go boom, 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 and then we sketch it in. Okay, holy moly, this one has a lot of stuff going on all together. But again, take it piece by piece. What is our period? Our period is 2 pi divided by the coefficient, which is pi. Pi's cancel. We get 2. So I'm going to say that I have 2, 1, 1/2, and 3/2. Okay, but we have a phase shift and a modified period, which means I need to factor this thing to figure out what my phase shift actually is. So factor out the pi, you're left with x plus 1/2. Okay, well that's cool because now our phase shift is in terms of the actual fraction which we're dealing with anyway. So that's sweet. So we get -3. Well, what does that 3 do? The 3 affects the amplitude, makes it 1, 2, 3, 1, 2, negative 3. So negative 3, positive 3. What does that negative in front do? Well, that makes sign go down first instead of up first. Okay, that phase shift of 1/2 is going to shift us to the left. So I'm going to put another tick mark right there, and that is where I will put my first point. 1 point right there. Need to go down first since it's negative, and boom, and boom, and boom. And then there you go. There's one period of that graph. I really like this. Once you start to understand it, they become really quick and honestly, I think kind of fun when you get this really complicated looking function. You can break it down piece by piece and it becomes very straightforward to graph. Okay, so here's an opportunity to see, again, a really messy one hopefully become a little bit easier. So let's see what we can do. All right. First things first, what's the period? Period is 2 pi divided by the coefficient, which is 1/2. So that's going to be the same as multiplying by the reciprocal. So we're going to get 4 pi. So the first thing I'm going to do is I'm going to say 4 pi, 2 pi, pi, and 3 pi. Okay, what's the next thing? Well, there's really no particular order you have to go about doing this in. I see that plus 2. It's going to shift me up by 2. Okay. I see this right here is going to make my amplitude 2, which means I actually need to go an additional 2 above that. And there you have that. The negative is going to flip it down. Let's worry about that in a moment because we need to figure out what our phase shift is. So we need to factor this. So we get 1/2 times x minus pi. Do you see that? Okay, so that means my dog's crying. I think she needs to go pee. Can you hear her? She's going, row. I'll go let her out. Hey, I'm also going to eat some food. Maybe a date. Okay, I lied. I didn't eat a date. I ate a watermelon fake Twizzler thing. It was sour, more sour than I thought it would be. But it was pretty good. And I put a microwavable Amy's enchilada, cheese and bean enchilada, into the microwave. And it's kind of funny. There are instructions that say, please, please do not overcook. So I'm hopefully not going to. I put it on half power as they suggested. It's the first time I've ever actually done that on a microwave, and I hope it turns out well. What were we talking about? Oh yeah, we factored it and we figured out that our phase shift is to the right by pi. Okay, so I know that my starting point is going to be lined up with pi. I'm dealing with a cosine function. Cosine normally starts at positive 1, but it's a negative 2 in front, so I'm going to start at negative 2, but I'm shifted up 2, so I'm going to start at 0. Wow, that was a lot. So I'm starting at my lowest point, which means now I need to go halfway there, and halfway there, well, to the top, and then there again, and, well, follow the pattern here. I'm going to go, whoa, boom, and hit right there. Cool. That's it, I think, unless I mess something up. I don't know, it's like really late. Maybe I did. Just one last one here we're going to do, and then we're totally going to stop. And this is going to be really cool how this one simplifies. I love it. Y equals, that's not what I wanted to do. What I want to do is I want to factor this inside. So I'm going to factor out that negative 2 pi, and I'm going to be left with x. Notice this is going to become x plus something. And it is clearly an indication of how late it is, because I can't, like, remember how to do this. Wow. This is sad, but happy, because it's been 4.5 minutes, so my enchilada is done with its first round of cooking, so I need to take the plastic overwrap off and mix my beans and then cook it for a minute and a half on high heat or until thoroughly hot throughout. Okay, come on, Rob, you can do this. I factored out a negative 2 pi from a negative pi, which means I've divided it by a negative 2 pi. So my negatives cancel, and my pi's cancel, and I'm left with 1/2. So I should get a plus 1/2 right there. Check it and make sure it's good. Is 1/2 times negative 2, negative 2 pi. Is that the same as negative pi? Well, let's see. We get negative 2 pi over 2. My 2's cancel, and I get negative pi. So it's good. It worked. I did it. I did math. Okay. But notice now we have a negative 2 pi inside that cosine function. And what type of a function is cosine? Cosine is even, which means that negativeness doesn't matter. Cosine of x and cosine of negative x will look exactly the same. It's even. That's what that symmetry means. That's 6. So this function is actually y equals negative 3 cosine of 2 pi x plus 1/2 plus 2. So now we need only piece it all together. So if the normal period is 2 pi, I need to divide that by my coefficient, which is 2 pi. So what do we get? 2 pi over 2 pi is 1. So I'm going to go whoosh, like that. I'm going to go 1, 2, 3, 4, 1. 1/2, 1/4. That's an awkward 1/4. 1/4, 3/4. Notice the plus 2 is going to shift everything up by 2. So I'm going to draw my line of symmetry right there. Notice the 3 is going to make my amplitude 3. So I need to go 1, 2, 3 above that line, and 1, 2, 3 below that line of symmetry. And I need to shift everything to the left by 1/2. So I need a tick mark there, and I need another tick mark all the way over here, because I'm shifting it by 1/2 to the left, because it says plus 1/2. Okie dokie. Oh, my dog's just crawling out from underneath my bed. She is adorable like that. I'm going to continue that line of symmetry over. So, normally cosine starts at positive 1. We're multiplying it by negative 3. So we're going to start, we would be starting down at negative 3, but we're adding 2. So we're going to start down at negative 1. So we're going to have our first point right there. And then we're just going to run through the cycle. So my next point needs to be on that axis of symmetry. So we have negative 1/4 right there. That's going to give me that point. My next point has to go up. My next point has to come back down. My next point has to continue down. And my next point has to go back up. And my next point has to continue up. And there we go. Whoop-de-dup. Now I can sketch it in. And my doggy is all up in my face and making this hard. And she's nosing my iPad. You're not making this. What are you doing? You cannot. Oh, fine. She wants to crawl into the blanket. She's a little baby. She needs to be tucked in. Go in. Go on. Here. Go. I just throw a blanket on her, and then she eventually settles down. Okay, well, that's my function. We're done. So, a little closure for once. What do the transformations do? And what do they do to the sine or cosine graph? Well, the A affects your amplitude, meaning how stretchy is your graph up and down, and it also can flip it vertically if it's negative. Okay, what does the B do? The B affects I want to say it's this type of effects. The B affects your period, which is t. And we can get our period, t, by saying the normal period for a sine or cosine graph divided by that b. Okay? What does the c do? Well, the c is your phase shift, which means it shifts it left if it's positive and right if it's negative. But if you have a phase shift and a modified period, you need to factor that b out of the c. So the phase shift would really become c over b, whatever that is then, to the left or to the right. I don't know why I said it reversed. Okay, and then the last one, d, well, that is just your vertical shift. It moves it up or down. What's the difference between sine and cosine? They are 90 degrees offset. There's sine and there. It's awkward trying to do both. And there's cosine. Done.